Many of the world's greatest railways have defied nature, overcoming its most difficult terrain. Whether scaling sheer heights or navigating dense forests, engineers have managed to carve out routes to create the most epic lines imaginable. But crossing chasms tests them to their limits. From ferocious rivers to remote windswept valleys, uniquely engineered bridges crucially keep the world connected. But each of these crossings throws up individual challenges that are often seemingly impossible for railways to overcome.
When you see that view, you can understand why it was so difficult to develop transport back in the 19th century.
The Rosa line was very difficult to construct because this valley is a close, narrow valley with steep hills.
Well, the key challenge is the tidal range. The water flows in and out of a quite constricted channel very fast.
But arguably the biggest obstacle facing bridge engineers is a hidden one. Bridges can help the railway overcome almost anything. They can conquer dizzying heights, span the longest lengths. But when it comes to crossing shaky ground, you need to think carefully before you continue. Located on the notorious Ring of Fire, New Zealand's brooding volcanoes are a stark reminder it sits squarely on a major fault line, where the Australian and Pacific tectonic plates collide. Here, the devastating effects of earthquakes are an ever-present threat. Heritage advisor Karen Astwood has travelled into its rugged interior to see how engineering played its part in keeping a vital railway safe from seismic shifts.
What I'm approaching now is one of the North Island main trunk original tunnels. When the line was constructed in the early 1900s, it became incredibly important because it connected Auckland and Wellington, which is the North Island's two major cities.
But by the 1960s, this particular section of the main trunk line in the Rangitiki district was putting the route in jeopardy. Many of the tunnels built were in danger of collapse.
Upgrading this section simply wasn't practical. The unstable ground meant the tunnels weren't feasible to strengthen, and neither was creating new ones.
Instead, engineers came up with an ambitious plan to reroute the original line, known as the Mangaweka deviation. But in the way lay what appeared to be an insurmountable obstacle.
This is the Rangitiki River, one of New Zealand's longest and most spectacular rivers.
Today, Karen's taking an entirely different form of transportation.
Hi, Karen.
Hey, I'm good, thank you.
To get an idea of the true scale of the problem.
I'm really looking forward to this. It's going to be great.
Get on, you can jump on the raft here.
The river here has carved a massive gorge. You can really get a sense of why the original railway line didn't go this way. So that's why they went with the tunnels. It was only in the late 20th century when they had the better technology available could they even attempted to cross this gorge.
And even then, it would still take an extraordinary feat of engineering ingenuity to do it.
And this is what I've been waiting for. Here it comes. This is the South Rangitiki Viaduct. It is immense. What an amazing structure. So impressive.
Opened in 1981 and measuring a staggering 315 metres in length, the mammoth six-span viaduct carries a single track across twin-legged piers, a vertigo-inducing 76 metres above the river.
Wow.
But to see what makes this bridge truly revolutionary, you need to look much closer to the ground.
When designing the South Ringatike Viaduct, engineers had to consider the earthquake conditions it needed to operate under to keep the critical North Island main trunk line functioning.
It was the groundbreaking work of eminent earthquake scientist and engineer Dr. Ivan Skinner which provided the answer.
At the time the Mangaweka deviation was being planned, seismic engineering technology was in its infancy. So the designers of the South Ringatike Viaduct had to come up with a completely new solution: base isolation.
The first of its kind in the world. The bridge's innovative design features energy-absorbing dampers in the foundations, which allow it to step from side to side when a tremor hits.
Okay, so we're just putting together a really basic demonstration to give you an idea about how base isolation works. To begin with, we've got a shake board, which is going to mimic the horizontal forces of an earthquake. Now, usually you'd build your bridge straight onto the earth. With the South Ringatike Viaduct, however, we've got the foundations, and then we've got the base isolation, then we've got the pier.
Unlike traditional bridges, the foundations consist of two sections. One built into the ground and the other fixed to the bottom of each pier. At the base of each pier sits a set of rubber pads, which act to absorb a portion of the energy created in the event of an earthquake.
So these tennis balls are standing in for the flexible bearings or pads that are in the base isolation. And this is a platform that the bridge pier is going to sit on. Okay, so now that we've got the foundations sorted out, we're going to build our piers. This is just a standard old bridge. Build it straight into the ground, onto the foundations. And here is a pier from the South Ringatike Viaduct. But to show you the full effect of how the base isolation works, I've just got to duck off and get some water.
Rather than rigidly fixing the bridge, the base isolators effectively separate it from the ground for greater flexibility.
Okay, so here comes an earthquake. And as you can see, the one straight into the ground is absorbing all of the energy from the earthquake, so it's more likely to fail and the bridge collapse. While the South Ringatike Viaduct, it's not absorbing as much of the earthquake forces, so it's less likely to fail in the event of an earthquake.
Under most circumstances, the bearing pads absorb enough force to keep the bridge structurally intact. But in a major earthquake, the pier can lift up by as much as 13 centimetres, allowing it to step from one leg to the other, preventing a catastrophic collapse.
And that's the genius of base isolation.
Every day, Ivan Skinner's inspired innovation enables trains to traverse the length of New Zealand's rugged North Island, keeping the country moving even when experiencing the most terrifying tremors.
Engineers weren't going to let earthquakes stop the railway. This is an ingenious piece of engineering, and I love it.
Many of the world's most impressive bridges were built to carry the railroads. Ingenious structures spanning the deepest chasms. Building bridges is a fundamental part of railway engineering, but arguably the biggest challenges are posed by the elements. When the weather's on your side, riding the railway is a sunny proposition. And when it comes to bridges, clear skies can make for pleasant crossings. Unfortunately, Mother Nature doesn't always play nice, and the consequences can be disastrous. Southern France's rugged Auvergne region isn't the most obvious place to build a railway. But at the end of the 19th century, transporting wine from the region's vineyards to the capital, Paris, became a priority. Forming a natural blockade, however, was the Massif Central, a sprawling landscape of imposing peaks, deep gorges, and famous for its strong winds. Historian Patricia Rocher is taking to the skies and taking on the notorious turbulence.
Wow.
To get a bird's eye view of why plans to build a new line had hit the buffers.
When you see that view from the plane, you can understand why it was so difficult to develop transport back in the 19th century.
For years, engineers had sought to conquer one particularly problematic obstacle: the immense Truyère River gorge.
The valley is very deep and very large. You had another difficulty, which was the wind. You know that wind makes tall buildings sway, and in a valley, the wind is stronger. So here in Garabi, it was really a challenge.
To combat the elements and bridge the valley would require a feat of engineering ingenuity: the breathtaking Garabi Viaduct.
Wow, what a wonderful view. It's really fantastic.
At 564 meters long and 122 meters high, upon its completion, Garabi was the tallest and longest railway bridge the world had ever seen.
You know, the first time that you come here in Garabi and you see this enormous structure, it's really a mind-blowing experience.
The iconic design of the Garabi Viaduct was the work of one of the 19th century's most celebrated engineers, Gustave Eiffel.
It was an exceptional site to build something, and that's why Eiffel was contacted, and he said, "Okay, I will do something here."
Eiffel's solution to withstanding the gusting winds is today being viewed up close by the maintenance team tasked with inspecting this mammoth structure. It's one that would go on to earn him the nickname the Magician of Iron.
The one factor was very important. He used structures with holes to let the wind go through. You can see on this viaduct the crosses, you know, and it's very typical of Eiffel style.
Instead of thick, solid girders, Eiffel used smaller, crisscrossing wrought iron beams with thousands of triangular gaps. His inspired design dramatically reduces wind resistance as it's buffeted by the powerful gusts at Garabi.
Just let me explain. You see here, the wind have no space to go through the structure and it fall down. Thanks to the hole in the structure, it's okay. You see, the wind can go through it.
Despite its lightweight appearance, the Garabi Viaduct was designed to carry a 400-ton train and built to last. The 165-meter-wide arch was constructed from both sides, as cranes at each end extended it piece by piece until the two halves were joined. Metal structures expert François Millien
On fera une pause, ouais, à ce niveau-là, là, au troisième palier.
is part of the fearless team responsible for ensuring the bridge continues to stand the test of time.
I remember the first time I was here, it was so impressive. Nobody can forget this.
Taking 5 weeks to complete, each of the bridge's crisscrossed beams and 600,000 rivets are inspected for signs of wear.
Yeah, of course, you know, when a train across the bridge, you know, we can feel all the vibrations. We just need to look if we don't have some fissures or cracks.
After another clean bill of health, this masterpiece is still standing strong against the brutal battering of the wind. Eiffel's little-known masterpiece of railway engineering remains a stunning example of his signature style, that would later inspire a Parisian icon, the Eiffel Tower.
It was a great achievement. This one is special because everybody in the world knows the Eiffel Tower, but they don't know this viaduct.
We still are very proud of this viaduct. It's a special feeling to see such a structure in the air, in the middle of the countryside. This viaduct is really a celebration of French engineering.
Railway crossings. Engineering marvels connecting some of the world's most thrilling journeys. Requiring unique designs and ingenious thinking. Historically, bridges have been built from many different materials, even in the most extreme of locations. Moving trains across mountains is never an easy task. To overcome the obstacles in your way, you'll normally need to build some bridges. But crossing heavy trains over vast valleys requires the right materials. And if what you've got isn't strong enough, you'll need to think again. Home to the towering Alps mountain range, Switzerland's impenetrable peaks would make train travel impossible. Were it not for the ingenuity and resourcefulness of its railway pioneers. Nowhere are the challenges they faced more obvious than the spectacular Rhaetian Railway. This iconic network of 10 lines clings to the steep slopes and valleys of the Swiss Graubünden canton. Today, bridge specialist Carl Baumann is taking to the tracks en route to a spot where early 20th century innovation helped conquer this most mountainous terrain.
Well, the network of Rhaetian Railway is about 400 kilometers long. We have 600 bridges, which have a length of 15 kilometers altogether. Makes about 4% of the whole net is over bridges. It's really special.
At its heart lies the Arosa Line, a 26-kilometre single-track railway which climbs a dizzying 1,000 metres through the Schanfigg Valley. Carl's destination is Langwies, where the forbidding Alpine setting presented rail engineers with what seemed like an impossible obstacle to overcome.
The Arosa Line was very difficult to construct because this valley, which is called Schanfigg, is a close, narrow valley with steep hills.
To make matters worse, here at Langwies it also has to cross the vast River Plessia gorge.
Here the line changes from the left side of the valley to the right side of the valley, and in a height of about 60 meters above the riverside.
For trains to cross that valley would take a feat of engineering on a truly epic scale. The daunting task fell to civil engineer Hermann Schursch. He not only needed to design a structure strong enough to span the huge chasm, it would call for a groundbreaking approach to how it was built too.
In the beginning of the century, most of the bridges were masonry bridges which are built out from stones. And here between Chur and Arosa, we have no such stones.
Given the steep terrain, transporting large sections of solid steel was out of the question.
Steel is not possible here because we had only the possibility to bring up 8-meter-long elements.
The solution was the mighty Langwieser Viaduct. Constructed from a material which had never been used to build a railway viaduct on this scale before. Reinforced concrete. At 284 meters long, with a central arching span 100 meters wide. When it was completed in 1914, it was the longest concrete railway bridge ever constructed.
Well, Langwies Viaduct is in my eyes the most impressive railway bridge, and it's one of the most interesting engineering construction when you look over the whole world. Of course, this is a very innovative bridge because it's a concrete bridge. Concrete with steel inside was a new material in that time. It's very modern construction also inside of today.
To build a bridge strong enough to sustain the weight of trains across the valley in a single arching span, Schurch embedded steel within the concrete members of his structure. By reinforcing the concrete in this way, he could make use of both material strengths. Steel to resist tensile or twisting forces, and concrete to resist compressive forces.
It was completely new design at that time.
Using a huge framework of wooden scaffolding for support, up to 200 men toiled on the project, ensuring its completion took just 2 years. Thanks to the vision and skill of the men who built the Langwies Viaduct, reinforced concrete conquered the giant gorge.
It's very impressive, and it's very great testimony to engineers of 100 years ago.
And changed the way rail bridges were built forever in the process.
When I stand here on the edge of Langwies Viaduct in Langwies, for me it's a very impressive construction. I'm very proud. It's a work of art, of course.
Across the world, pioneers have engineered new materials to create crossings. But in other locations, resources may be abundant, but the design takes some inspired thinking. When it comes to building bridges, using piers and foundations is normally a winner. But what happens when there's water in your way? Tides and currents can make things tricky. Meaning the only way to cross is to take your bridge design back to the drawing board. In the 19th century, engineers faced the challenge of building a faster route connecting London and Dublin. In order to connect the two capitals, a new rail line would be needed that would run along the north coast of Wales. But to achieve this ambition would involve bridging a deceptively difficult stretch of water. The gaping Conway River estuary and its complex tidal flows. The obvious place for a crossing was at the river's narrowest point, where Conway's imposing castle had been strategically built around 600 years earlier. But as civil engineer John Chilton appreciates, turning the idea into a reality would test engineers to their limits.
Well, the key challenges for building a bridge in this sort of situation is very fast-flowing river. The tidal range means that the water flows in and out of a quite constricted channel very fast.
Adding to the titanic challenge, it would need to bridge the entire river in a single self-supporting span, a feat seemingly impossible for the technology of the 1800s.
If the engineers were going to put a bridge across at this point, then they would have to have a particularly revolutionary solution to take these heavy loads across.
Their answer was the groundbreaking Conway Railway Bridge. The first box girder bridge ever constructed. Complete with formidable towers designed to blend seamlessly with its medieval neighbour. This pair of wrought iron tunnel-like structures weigh in at a massive 1,320 tons apiece. And stretching 129 metres across, when it opened in 1849, it was the longest single-span rail bridge in the world.
The key thing here is that you're taking the railway bridge to much larger dimensions. It certainly was a groundbreaker at the time.
It was the brainchild of two of Victorian Britain's most eminent engineers, Robert Stephenson and William Fairbairn. To eliminate the need for central supports, Stephenson's inspired idea was to carry trains through his bridge, rather than over the top of it. But the size of the span needed would push the boundaries of Victorian engineering like never before.
To show the principle of a girder, we've got two piers of the bridge here. We have a girder, this piece of paper, which is very thin and wide. And if we put it across between the piers, it sags and won't even carry its own weight. The strength of the girder depends principally on its depth.
To construct a girder strong enough, Stephenson and Fairbairn experimented with different shaped tubes.
So the circular section already holds its own weight, and it will carry this little pot at the bottom here. I'm going to add some pennies to demonstrate how the beam works. 1, 2, 3, 4, 5, 70, 71, 72. And as you can see, the tubular beam has failed by crumpling.
With only a small point of contact between beam and piers, load stresses cause it to squash at the ends.
So now we're going to take this rectangular tube and see if it outperforms the circular tube, which failed at 71 pennies. 72, 73, 74, 75, 101, 102, 3, 4.
Having a larger surface area in contact with the supports each side of the river meant Stephenson and Fairbairn's box girders could carry significantly more weight over a longer, single span. But overcoming the monumental challenge of crossing the River Conway didn't stop at the bridge's design. Constructing the enormously heavy spans in mid-air over the water wasn't an option.
If you have the high tidal range and you have fast-flowing water, it makes it difficult to put temporary supports in the channel.
Instead, its engineers turned to nature and ingeniously turned the Conway's treacherous tides to their own advantage.
The girder, made of wrought iron sheets and angles riveted together, was constructed on a beach nearby between the high and low tide marks.
Once complete, large pontoons were floated underneath so it could be towed into position and lifted into place with hydraulic pumps.
The high tidal range was actually used for the benefit of the construction process. As an engineer, I absolutely admire the teamwork that went into building this innovative bridge.
For its time, the Conway Bridge was a radical piece of railway engineering. By introducing the new box girder technology, it pushed the boundaries of what was thought possible and changed the face of bridge building forever.
The Conway Bridge certainly moved the technology forward because this form of bridge construction has gone on to influence the design of long-span bridge beams worldwide.
And this groundbreaking feat of ingenuity is still part of Britain's busy rail network today.
The Conway Bridge is a magnificent achievement. The fact that it is still standing here after 170 years is a testament to the quality of the Victorian engineering, and this certainly has stood the test of time.
Over centuries, pioneering engineers have built some of the world's most impressive railway crossings, making it possible for trains to conquer deep valleys, scale harsh mountain terrain, and cross wide tidal waters. But some of the most inspiring structures have been built from the very loads that trains travelling across them once carried. Sometimes crossing chasms can be the least of a bridge builder's problems. If you're working in the wild, getting materials to site can be a real slog. And if all that dragging and lifting gets too much, there might just be an answer that's closer than you think. At the start of the 20th century, the global market for timber was sky high. While Canada's densely forested Vancouver Island offered apparently endless resources to meet the demand. Transporting vast loads of lumber from this remote spot to the mainland and beyond presented an impossible challenge. A problem islander and master carpenter Gord MacDonald understands well.
This is Cowichan Bay, and Cowichan Bay is really the gateway for logs for this island, and it has been for centuries. It's getting them to here is the tough part.
In 1911, a railway was commissioned to carry wood from the logging camps to the coast, but building it would prove to be anything but easy.
100 years ago, you can just imagine how difficult it was to build in this sort of geography. Vancouver Island is very up and down, these long inlets that cut for miles and miles inland.
After extensive surveys, a route was finally chosen. One which left engineers facing what seemed like an impassable obstacle. The plunging Coxilla River Gorge.
Even on a summer day like today, you can hear the river below. And in winter, the water just chucks it down this valley, along the riverbeds, through almost impenetrable forests.
But trees had brought railway builders to the island, and it would be trees which provided a solution to bridging the huge ravine.
Once the decision was made to make a crossing, then the choices were really timber bridge or steel bridge. It's just sensible that you would prefer to use materials which are locally available.
Conquering nature with the simple resources on hand would take a truly remarkable feat of engineering. The monumental Kinsole Trestle. Standing 44 meters high and spanning 188 meters in length. The Kinsole Trestle took an incredible 1.2 million board feet of timber to construct, making it one of the largest wooden bridges in the world.
I must say, even though I've been here hundreds of times, it always is a real treat to come back. It's such a great bridge.
The wooden trestle was a vital part of Vancouver Island's valuable logging industry for nearly 60 years.
The Kinsole is really a unique bit of engineering. You've got this quite ambitious crossing, the deep side here, complexity of the shape.
A problem made worse each spring as the river levels swell with melting snow and ice, putting the timber to the test.
You can tell just by looking at it that it was really built to perform heavy work. There's a section of the bridge which is quite long and has to be kept up above the highest water. That section of the bridge has to be entirely self-supporting. You can't build in the in-canal section or in the river section because, of course, it would just be swept away.
To see just how the wood was engineered to conquer the river requires burrowing to the very heart of the bridge.
All the bears around here are vegetarians, I think. You should be reasonably safe. So where we are now is down in the very working guts of the trestle. We're just making our way out into the Howe trusses.
First patented by American bridge builder William Howe in 1840. His ingenious design made it possible to build bigger spans using wood, something in plentiful supply here.
Howe trusses were great for these logging bridges because not only did they use a lot of wood, but you could use relatively small pieces or short pieces of wood.
In a truss, the three sides work together to give it strength. In a Howe truss, the diagonal wooden beams leaning towards the centre of the bridge are in compression, while the vertical metal poles are in tension.
So generally in the web of the truss, the timber is doing what it's best at. It's working hard in compression. The other big advantage of a truss like this is that it's also capable of a great deal of work over that long span. So it can carry a heavy load above and make a big crossing.
Today, Gord is going to check just how well they're holding up after almost a century.
So this is a tool called a resistograph, and it's a very slender drill. And as the drill advances, the onboard computer takes measurements of resistance. And we know that resistance is an indicator of wood strength.
Boring into the timbers at key locations reveals if they are sound or suffering from decay.
Imagine that that scale represents the path of the drill bit. And these peaks are measurements of high resistance, and the flat spots like that, that's probably the very center of the tree, the pith, will be less resistance. So, clean bill of health.
Although standing strong today, when the bridge closed in 1979, it quickly fell into serious disrepair. And in 2006, it was set for demolition. But after 4 years of painstaking restoration, the trestle was reopened as the centerpiece of one of Vancouver Island's most popular tourist trails.
People come from all over the world to see the bridge. They get an insight into just that age in the development of the West, when no task was too big and no undertaking too formidable.
And nearly 100 years after its completion, the Kinsale Trestle remains a towering achievement in rail engineering.
These sorts of bridges were just they're just a critical part of the railway, getting things from A to B. And one of the reasons we love them so much is because they just speak to that challenge overcome.
The world's engineers are continuously pushing boundaries. And in the 21st century, there's one mega bridge in the making that will be capable of conquering all. India. Home to some of the world's remotest communities. None more so than a region within Jammu and Kashmir, bordering Pakistan at the foothills of the Himalayas. And it's here that a record-breaking railway project of epic proportions is underway.
The region around Bakal and Kauri is very, very remote, and it's very difficult to get around there. And so for a long time, there's been this will or this need to create a railway link.
The Kashmir Railway project is a 345-kilometre line that will connect communities amidst some of the most hostile terrain on Earth.
That rail line has to go through tunnels and above bridges because of the really mountainous topography that we experience in the Himalayas.
But in its path to completion lies a ferocious obstacle.
One of the trickiest segments of the entire line is where the railway has to actually cross over the river Chenab, and that's because the gorge is very, very deep there. So the distance from where the railway line is down to the surface of the river is over 300 meters.
The only way of spanning this enormous chasm is with the world's highest railway crossing, the audacious Chenab Bridge. At a staggering 1,315 meters long and towering 359 meters above the river, once completed, the Chenab is set to be a true giant of engineering.
The Chenab Bridge is a record in the making because once it's finished, it will be the highest railway bridge in the world.
But the most crucial phase of this epic project so far has taken place more than 100 meters below the valley's edge, preparing its foundations. No mean feat for a bridge of this magnitude.
The bridge itself is only as strong and stable as the foundations upon which it's built.
Engineering geologist Phil Ward has first-hand experience of dealing with the challenges facing the construction of the Chenab Bridge, not least because of its remote location.
When I first visited the site, it was a 6-hour jeep drive from Jammu up to the bridge site. The access roads were subject to landslides. The Chenab Bridge is crossing the Chenab River at a location where the slope angles are particularly steep, and surrounding the area of the bridge there's a lot of evidence of big landslides, so slope instability along the river gorge.
It took 2 critical years of boring into the steep slopes to analyse the condition of the rock before engineers were satisfied that the bridge foundations could be constructed. Then, the colossal process of stabilising the rock faces began.
These were the largest cut slopes I've ever been involved in, and a great deal of rock had to be excavated, and very, very large numbers of rock bolts had to be installed to stabilise those cut slopes.
Rock bolts are formed from grids of steel bars, some up to 40 metres in length, that are driven into the rock face and secured in position. Once inserted, the bolts help stabilise and strengthen the valley's walls, creating a surface that's secure enough to build on.
These reinforced the rock mass and gave us assurance that we could provide an adequate factor of safety on slope stability.
Over a decade since its conception, the vast gorge is almost ready for the arch to span the river. However, this project still has years ahead of it, and many more obstacles to overcome before the bridge and this ambitious railway line is complete. The giant arch will need to withstand all that this volatile region can throw at it, from earthquakes to destructive winds and monsoon rains. But once complete, this monumental structure will dwarf the Eiffel Tower and set a new benchmark for mega bridges around the globe.
For me, this has been one of the most exciting projects I've ever worked on. The scale of the project is mind-boggling in actual fact, and it always amazes me every time I visit the site as I come around the corner on the access road and see these massive rock faces dwarfing the tiny little vehicles that are traversing the faces.
This project is testing engineers to the limit and will surely continue to do so. Meanwhile, the world watches challenge after challenge overcome.
I think it is so fascinating watching the progress of a record-breaking bridge like the Chenab Bridge. And I also think it's a real jewel in the crown for structures in India because it's had so many different complex challenges solved that it will almost set a precedent. Once this bridge is finished, I think it'll be one of the most impressive bridges in the world. It's a really, really impressive structure.
Since the birth of the railways, bridges have opened up the world to trains. Allowing them to cross seemingly unconquerable chasms.
I hope at some point in the future I can travel across the Chenab Bridge and feel privileged that I was involved in the design.
Thanks to inspired solutions.
The base isolation used in the South Ringatike viaduct was completely innovative at the time.
Engineers continue to build their impossible railways.
Every time we push a boundary, we then aspire to push that boundary even more, to break that next record.